Hello everybody, back to power electronics module number 3, inverter and AC voltage controller. We're still in an inverter part. Okay, today I will talk about last type of inverter in single phase, and then I move to three phase inverter. Okay, now the push-pull inverter is another single phase inverter, but rather than we use 4 switches. Okay, we use only 2 switches, but we would use at the same time transformer, okay, center tab at the primary side. You mean the primary side here you have center, okay, here in this way. How the circuit work? Have a look. Definitely these diodes are the freewheeling diodes connected in anti-parallel with the thyristor as you explained before. And let's assume T1 will conduct, T2 should be off. At any instant of time, one of these switches will conduct. So current will follow here, as you can see here, following here, back to the supply. You see? Now this sold point, okay, just to show you the polarity, as example here, it will be plus, minus, the negative part on the solid point will be negative here, positive here, okay? Now let me change the color. Let's take blue. Now let's assume now the second part of the time T2 will conduct. The current will follow here, here, through this switch back to the supply in this way. So here is the positive, here is the negative. So positive here, negative. Oh, it seemed to be the polarity changed. It was positive, negative, positive, become negative, positive, negative. So we have changed. Then we got either the square wave or the pulse width modulation. It can work in either way. Okay. The same discussion before apply for full bridge is apply here. Output voltage is MA VD. By the way, we divide it by N, the turn ratio, just in case if there is turn ratio. If it is 1 to 1, that's it, done. It's okay. This is for MA lower than 1, linear. For greater than 1 over modulation, the same discussion also. V output fundamental greater than VD, lower than 4 over pi because square wave. One more point to be mentioned here, that the switch should handle, and switch an instant of time to handle the supply voltage and the voltage back, because here it will introduce in the other winding voltage, so it have to handle double of the voltage for the supply. The formula is divided by current. Current usually higher than the value we use, okay, we supposed to use. Why? For many reasons I will mention, but when current increase, switch utilization will go down. So this 0.16 will be lower. It will be lower than 0.16. 1.6 means 16% of the time using the switch. Why we have to use higher current? The rating, usually when we want to design our circuit, we select the current. When we do the calculation, example 10 ampere, we add 1 or 2 ampere extra just for safety, for the worst situation if extra current coming from anywhere in the circuit. Also, the variation of the input voltage, you know, the input voltage coming from a supply, okay, so any change in the current or in the pulse width current, change in the current due to the pulse width modulation will increase the current and reduce the switching utilization factor. The ripple in the output also affect, and sometimes we may work with overload. If overload came, then the current will be high again and the switch utilization factor will be low. Now this previous discussion was for square wave. What if we want to discuss it in terms of pulse width modulation? For pulse width modulation, definitely we need to multiply by pi over 4. And when we multiply it, okay, you see here, we multiply by over 4, the switch utilization will go more down than the previous one. It's a small time to be contributed by the switch from the whole period. Let me use this in example. A single phase full bridge pulse width modulation inverter. VD, the input, change between 295 to 325. The output voltage is required to be constant, 200. He told me this is RMS. And the maximum long current assumed to be sinusoidal, 10 amp, also RMS. calculate the combined switch utilization ratio under these idealized conditions, not accounting for any overcurrent capability. Now for the switch, it is, don't forget, single phase fully bridge. For the switch, it handles the full voltage. We take the highest, okay, which is the worst situation. IT, the switch current, is square root 2 IO. I got it, okay, the maximum, because here RMS, I need to multiply by square root to go the maximum. It's fully bridge, so I expect Q to be 4 switches. And VO1 IO max is 200 by 10. He gave me both. Now let me substitute and do the calculation. It's 0.11. You remember the number, previous number in the previous slide? 0.16. Now it's 0.11. I told you it's lower than the expected one. Now after we complete a single phase, let's go for a 3-phase. Before I go for 3-phase, just to make it very simple for you, what we have, rather than one leg, we will have another 2 legs. So this is leg A, leg B, leg C. And we would control them to make sure that 120 phase shift is the phase shift between each voltages coming from different legs. Now for pulse width modulation inverter, as you can see here, we will have sinusoidal for V control for A, for B, for C. And since the control is 120 phase shift between them, the output expected to have 120 between them. If I take 2 legs, VAN and VBN, VAB is the difference between them. Similar to the discussion we done before in